Alright, well, welcome back everyone. In this video, we're going to introduce AC power and complex power. Here's our goals for today's video. First, we're going to learn that there's actually several different flavors of AC power. So first, we're going to explain the similarities and differences between power in AC and DC circuits. And then we're going to learn how to calculate the different kinds of AC power, including instantaneous power, average power, complex power, and RMS power. And finally, we'll start applying complex power, RMS, and instantaneous power to solve different kinds of circuits problems. So let's briefly remind ourselves where we are heading. At this point in the course, we have already learned a lot of tools to help us solve AC and DC circuits. So now we are shifting our focus to study important applications of circuits and various types of electrical devices. In our previous video, you'll remember that we covered frequency response and filters. In this video, we're going to introduce AC power and complex power. Then in our next video, we're going to focus more on specifics including power factor correction, and maximum power transfer. Finally, our last topics will cover power distribution, transformers, and devices. Let's go ahead and do a quick review question before we move on to AC power. So here we are given a circuit that has an AC voltage source, and we're given that the voltage source is a sinusoidal source with amplitude 25 volts. We are also told that our resistor is a 20 ohm resistor. So in this question, we are asked to find our current I of t and voltage V of t delivered to our 20 ohm resistor. Then we need to determine the power delivered to that resistor. We're also given a hint that a trig identity might be helpful for us as we complete this question. So let's give this a try. Well, in this case, we're first being asked to determine current and voltage delivered to our 20 ohm resistor. So let's go ahead and start there. Well, in this case, we are already given V of t. Notice the only thing in our circuit besides our source is that resistor. So we know that V of t for our resistor is just going to be our source, as there's nothing else in our circuit. So in this case, we can say that the voltage source is delivering all of its voltage to our resistor. So therefore, the voltage delivered to our 20 ohm resistor is just 25 cosine 125t plus 45 degrees. Okay, so we know the voltage delivered to our resistor. We also know that our resistance is 20 ohms. So, if we know V of t and R, how can we find our current I? Well, in this case, the easiest way to find our current is just to use Ohm's law. We know voltage is current times resistance, so our current must be our voltage divided by resistance. So in this case, notice since our resistance is just 20 ohms, all we have to do is divide our voltage by 20. So in this case, we just divide by 20 ohms. So 25 divided by 20 ohms, that will give us 1.25 cosine 125t plus 45 degrees, and units here are amperes. Okay, so we found our current and our voltage delivered to our resistor. Our next question is to determine power delivered to that resistor. So how do we determine power? Well, you might remember our power, P of t, is just current times voltage. So in this case, we just need to substitute in and multiply current and voltage in order to find our power. Let's give this a try. So let's remind ourselves what we know. We know power is current times voltage, and we know our voltage, V of t, across our resistor is just 25 cosine 125t plus 45 degrees. And we know our current is just voltage divided by 20 in this case, or 1.25 cosine 125t plus 45 degrees. And so in this case, we would need to multiply those two sinusoids together. But it can be a little tricky to multiply a cosine times a cosine. We could end up with some cosine squared components, and things might get a little funny. But you'll remember we were given that trig identity. Let's use our trig identity to help us. You'll remember, if we have cosine A times cosine B, trig identity tells us that is equal to 1/2 cosine A plus B plus cosine A minus B. So in this case, our power is the product of voltage and current, or 25 times 1¼ times cosine 125t plus 45 degrees times cosine 125t plus 45 degrees. So in this case, notice I can go ahead and treat 125t plus 45 degrees as my A, 125t plus 45 degrees as my B, and I can apply the trig identity. And if I do that, I'll get that my power is equal to, here I still have 25 and 1.25, those are just constants. But then I replace cosine A cosine B with our trig identity. So I replace these two terms with 1/2 cosine A plus B plus cosine A minus B. And notice what happens when we substitute. We get 25 times 1.25 divided by 2 times cosine A plus B. That gives us cosine 125t plus 45 degrees plus 125t plus 45 degrees. Notice this is my A term, and this is my B term. And then now I have to subtract them in the second part of the trig identity. And so notice what happens. We can actually combine those A and B terms. And we're going to determine that our power is equal to 25 times 1 1/4 over 2. That's 15.625. And then look what happens here. Our frequency is going to double. We'll have cosine of 250t plus 90 degrees. And then, second term, look what happens here. A and B are equal. So that second term becomes a constant, cosine of 0. So therefore, our power becomes 15.625 cosine 250t plus 90 degrees plus cosine 0 times 15.625 gives us 15.625. And that is our power as a function of time. So in the rest of today's class, we're going to take a closer look at how AC power works and how we can use AC power and sinusoids to help us solve circuits problems. All right, so let's just briefly remind ourselves, what is power? You'll remember from the beginning of this course that we define power as the rate at which energy is supplied or absorbed. And so power is the time derivative of work with respect to time. Or we can write power as the product of current times voltage. You might also remember that water wheel analogy. It turns out that this is still applicable to AC circuits as well as DC circuits. So once again, with AC circuits, we do assume that the passive convention still applies. So if our current is entering the positive terminal of our circuit element, we say that positive power means power is being absorbed by that circuit element. And similarly, we say that our power is negative if our circuit element is supplying. So the passive convention still works with both AC and DC circuits. There's a few important differences between AC power and DC power. Remember, in AC circuits, our voltage and current are typically sinusoidal. And so if our power is positive and passive convention is satisfied, we are absorbing energy. And if our power is negative and passive convention is satisfied, that means we are supplying energy. So in AC power applications, it's very important to pay attention to when our power is negative or positive, because that polarity can influence whether we are absorbing or supplying at that point in time. So that brings us to another question. How would we be able to compare AC and DC values? Remember, AC values are sinusoidal. And so, depending on where I look along my sinusoidal signal, sometimes my AC value is higher than my DC value. Other times, my AC value might be lower compared to the DC value. So, looking at an AC value at a single point in time might not provide us enough information in order to accurately compare it with a DC value. So, to overcome this issue, we define this new concept of an effective value, also known as RMS, or root mean squared. RMS helps us accurately compare AC values with DC values. So let's provide a little bit of context to what RMS actually is. RMS means root mean squared, and it's basically a way for us to average an AC signal into its equivalent DC value. And so if you look at a standard US power outlet, you would see that frequency is 60 Hertz, and notice we specify our AC power as 120 volts RMS. That means the root mean squared value of our standard power outlet is 120 volts. Also, if we were using a multimeter like in the lab, we would see that if we set our multimeter to DC voltage or DC current, it will give us the average value of that voltage or current. But if we set our multimeter to measure AC voltage or AC current, we're actually going to see the RMS value of that voltage or current. Here's how we actually calculate that RMS or effective value. So by definition, the effective value of a voltage or current is given by the square root of the average of its value squared. That's why they call it root mean squared. You're taking the square root of the mean squared. And so here what we do is we take an integral to average the sinusoid's behavior over a full period t. And that allows us to get our mean value. Then we take the integral such that we get the average, and then we take our square root. And so therefore, by doing this root mean squared calculation, we can say that the effective value, or RMS value, is the steady state DC value that transfers the same average power as the AC value. So by calculating RMS, we can accurately compare an AC circuit's output to the output from an equivalent DC circuit. Sometimes we also see special notation when working with RMS values. So if you see the little tilde on top of the V or the I, that is also indicating that that value is the root mean square value. So it turns out there's also a nice shortcut. Suppose you happen to have a sinusoidal signal. If you use trig identities, you can derive that the RMS, or effective power, is calculated by taking the sinusoid's amplitude and dividing by square root of 2. So remember, when we say sinusoidal, that means it must be a sine or cosine. So in this case, if I have a cosine signal and I have some amplitude Im or Vm, I can say that my root mean squared value is that magnitude divided by square root of 2, or approximately 0.7707 times that value. But remember, these shortcuts are only valid for sinusoidal signals. If I do not have a sinusoidal signal, then I have to use these equations on my previous slide. So these equations will work for any signal, and then the shortcut works for sinusoidal signals only. Let's go ahead and try a couple examples of calculating RMS power. In this first example, we're given this sort of square wave looking signal, and we want to find the RMS value. In this case, since it's voltage, we'll find the RMS voltage of the waveform. So in this case, this waveform is a periodic signal, but it is not sinusoidal. So in this case, since it's not sinusoidal, we can't use that nice shortcut. So to find the RMS voltage, we have to use that equation with the integral. So remember, our equation is our square root of 1 over our period times the integral from 0 to our period of v squared dt. So let's first ask ourselves, what is v of t and what is t? Well, t is our period. And remember, period is just the time for one cycle. So in this case, I can determine that t is just going to be 3 seconds. Now let's think about v of t. So notice we can say that v of t is going to be 10 from 0 to 2 seconds. And then from 2 to 3 seconds, v of t is equal to 5. So using this information, we can go ahead and substitute into that integral. So we can say v effective is square root of 1 over 3 times the integral from 0 to 3 of v of t squared dt. Or, notice we can split the integral into a sum, where we have from 0 to 2 seconds, v of t is 10, and then from 2 to 3 seconds, v of t is 5. So all that's left is to calculate our integrals and take the square root. So the integral of 10 dt, be careful here. I forgot to keep my squares in there. Remember, it's v of t squared. So here we have 10 squared dt, and here we have 5 squared dt. So if we take that integral, 100t from 0 to 2, plus 25t from t equals 2 to t equals 3. So if we simplify that out, that becomes square root of 1/3 times 200 plus 25, or square root of 1/3 times 225, which gives us square root of 75, or about 8.66 volts. And if you think about it, on average that makes sense. Because if I were to draw a line at about 8.66 volts, you'd see that on average that sinusoid produces about that much DC voltage. Let's go ahead and try a second example. Here we are being asked to find the RMS value for the signal I of t equals 2 minus 4 cosine 2t. Here's an important strategy. We can treat this sinusoid, or treat this signal as a 2 amp signal and 4 cosine 2t signal separately. What we can do is find the RMS value for the 2 amp and 4 cosine 2t alone, and then look what we can do. We can write that our I effective squared must be equal to the I effective of the 2 amp signal squared plus the I effective of the 4 cosine 2t squared. And so by taking the two signals alone, we can plug them in to this general equation and find the RMS value of the sum. Let's give this a try. So once again, we'll consider the 2 amp source and the 4 cosine 2t source separately. So notice the 2 amp source is not sinusoidal. But notice that the 2 amp source is constant. So we can say our I effective of the 2 amp source is just going to be 2 amps. If you didn't immediately recognize this, you could still plug into the equation as normal, and you would see that we would just take the square root of 1 over t of our 2 amp source, and notice what we would end up getting is the same result. We'd have 1 over t times 4t, and that would give us square root of 4, or 2 amperes. So we've completed the calculation for the 2 amp source. Now let's consider the 4 cosine 2t source. Notice this source is sinusoidal, so we can use the shortcut. So remember the shortcut. We can say our RMS value is equal to our magnitude divided by square root of 2. So in this case, we have our amplitude of our signal is 4 divided by square root of 2. That gives us 2.828 amperes. And now all that's left is to take our total and plug back into that equation. So we add those together, we get 12 amperes. And so that means our RMS value is square root of 12, or 2 times the square root of 3 amperes. So now we've covered RMS power. Let's now talk about another kind of AC power called instantaneous power. We've actually worked with instantaneous power already. Instantaneous power, or P of t, is the power delivered by our AC circuit at any time t. And we can derive that if we have a voltage given by a sinusoidal signal Vm cosine omega t plus theta v, and if we have a current given by Im cosine omega t plus theta I, we can plug into that trig identity from earlier, and we can show that our instantaneous power is going to be given by the sum of two terms. Notice what happens here. The first term in our instantaneous power will be a constant. Notice there's no time dependence in that first term. That first term gives us the average power delivered by the signal at any time t. It's not time dependent, so we're always going to deliver the average power. But because our signals are sinusoidal, there's also a time-dependent portion. Notice the time-dependent portion is actually the frequency doubled from the original inputs. And so this gives us the time-dependent part of instantaneous power. So at any time t, our instantaneous power P of t is equal to some average power plus a time-dependent term. And so if you were to make a plot in MATLAB just to illustrate this, you can see that interesting things happen. Suppose I had two sinusoids. You'll notice in this case, I have this red sinusoid. This is 8 cosine 200t 70 pi over 180. So notice I had to write my phase angle in radians for the purpose of this plot. Otherwise, MATLAB would produce an incorrect result. So I wrote my degrees here as 70 pi over 180. Similarly, the blue curve in this example, so you can see the blue line in this plot is 5 cosine 200t. Notice if I plot the product, we'll see that the average value is not equal to 0. average value is something greater than 0. And the product's frequency is double the frequency of the inputs. So that happens because of the trig identity and because of constructive and destructive interference between the two input sinusoids. So once again, if we take a look at our instantaneous power equation, we can write that the average power is given by the non-time dependent part of instantaneous power. And another thing you'll notice about average power is its value depends heavily on cosine theta v minus theta I. This quantity is called the power factor. And we'll discuss this more in the next video. So before we do an example, let's briefly summarize the different kinds of power that we have covered so far. As you can see in an AC circuit, there's a few different flavors. We first covered that RMS power, or effective power value. Then we also have instantaneous power, P of t, and that's given by the product of our current and voltage. And you can also plug into the trig identity to get the full instantaneous power equation for a given current and voltage sinusoidal input. So if I know my voltage and current are given by the sinusoids listed here, I can plug in my magnitude and phase angle to determine my instantaneous power at that given time. We also covered the average power. Remember, the average power is the average power over a complete cycle of that sinusoidal wave. Average power is always going to be real, and we can say that it's given by the non-time dependent part of our instantaneous power. Suppose we wanted to find how much power was delivered to an element with impedance Z. So because of the RMS, or root mean squared, you see that power is equal to I squared times resistance. So if we plug in the RMS value for current, we determine that power is our current magnitude divided by 2 times the real part of our impedance. So notice there is this division by 2 that happens, and that's because of averaging and the RMS value of our power. One more important term to bring up is impedance. We mentioned just a moment ago that for average power delivered to an impedance, we take just the real part of our impedance in that calculation. So it turns out that impedance, you'll remember, is a complex number, and we can write impedance as the sum of a real part, R, plus an imaginary part, X. So notice if Z equals R plus JX, where J is square root of -1, the real part of impedance is called the resistance. And that's the same resistance that we know from DC circuits. But remember that AC circuits can also have imaginary components. So the imaginary part of impedance, X, is called the reactance. So Z, R, and X, all of those terms have ohms units. And if you ever find yourself working with admittance, remember admittance is the inverse of impedance, there are some analogous terms where the real part G is our conductance. Again, same thing as the conductance of a DC circuit. And the imaginary part B is our susceptance. And just like with conductance in a DC circuit, we say that admittance is measured in Siemens units. For the purposes of this class, we primarily deal with impedance, and we don't usually work with admittance, but it's included here for your reference. Let's do a quick example about instantaneous power. You'll remember this example is the same circuit that we looked at the very beginning of this video. So in this case, we know the voltage source delivers A cosine 125t plus 45 degrees volts, where A is 25 volts, resistor is 20 ohms. We're being asked to determine instantaneous power delivered to the resistor and average power delivered to the resistor in watts. So we've actually already looked at this circuit in our example from the beginning of the class. But notice we can also use our instantaneous power equation as a shortcut. So you remember we know V of t already. V of t is given as 25 cosine 125t plus 45 degrees volts. And I of t is just V of t divided by 20, or 1.25 cosine 125t plus 45 degrees amperes. And so in this case, another way to approach this problem is to immediately extract the magnitude and the phase angle of each term. And if we use Vm as 25 volts, theta V as 45 degrees, Im as 1.25 amps, and theta I as 45 degrees, we can plug in to the instantaneous power general equation. So remember from before we have this P of t equation, so we can actually just plug in Vm, Im, theta V, and theta I. And if we do that, we will determine that our power is equal to, we get 15.625 times cosine 250t plus 90 degrees plus 15.625. So notice this is the same result as when we use the trig identities. So that's our instantaneous power. What's our average power in this case? Remember, average power is just the non-time dependent part of the instantaneous power. So in this case, we see that our average power will be 15.625 watts, and our instantaneous power is that full P of t expression. So definitely keep those equations handy, especially the instantaneous power sinusoidal equation and our other equations for average and RMS power. They definitely come in handy in questions like these. Alright, so far we have talked about average power and instantaneous power, but everything so far has been in time domain. And so an important question comes up. What happens if we want to transform AC power into frequency domain? Remember, we often need to transform our circuits to frequency domain in order to find unknown values. So can we just take P of t and write a power phasor? It turns out that we can't just directly create this power phasor, but we can do something else. In order to look at power in frequency domain, we define a new type of power called complex power. Notice that we define complex power as the value S. So not P, because P is already used for real power. So we use S as our symbol for complex power. And we define complex power as the sum of this term P, which is our real power, plus some imaginary component. And notice that because complex power is a complex number, we can also write it as a polar form complex number, S angle theta, where theta is the phase angle of that complex power phasor. So complex power is really important in AC circuits. Complex power allows us to account for imaginary contributions from inductors and capacitors. If we don't create complex power, and if we only look at real power, we would be ignoring all the complex contributions from inductors and capacitors, and our results would be inaccurate. So, in order to study power in AC circuits, we also have to study the imaginary part and use complex power to help us do that. So I went ahead and summarized our complex power into this handy table. I call these very important complex power terms because they are indeed very important. Definitely keep this table handy. I guarantee you that one or more of these equations will definitely appear on the final exam in this course. So first we define our complex power S as the power absorbed or generated in the frequency domain. And notice that complex power is written using our current and voltage phasors. Here is a very, very, very important equation. If we want to calculate complex power, one of the most important equations we generally use is this one that I've circled here. Complex power S is equal to our voltage phasor times complex conjugate of our current phasor. Notice the star. Remember, complex conjugate, we just have to flip the sign on the imaginary part. So we take voltage times complex conjugate of current divided by 2. That will give us our complex power S. In polar form, we can also write complex power as our magnitudes, voltage, and current divided by 2, angle theta v minus theta I. So if we are given some current and voltage sinusoids, we can directly plug in and determine complex power if we know our magnitudes and phase angles. there's a few more important terms related to complex power. First one is the apparent power. Apparent power is the magnitude of the complex power. So if I write complex power as S angle theta, the magnitude would be our value S. So we can calculate S as just Vm Im divided by 2, where Vm and Im are the magnitudes of our current and voltage phasors, and divide those by 2. Remember, that's just the magnitude of the complex power, so this part is only that S term. It does not include the phase angle. Next is the power factor angle theta. So if I write my complex power in polar form, theta is our phase angle of the complex power. So we call that our power factor angle. We'll see later on that this power factor angle is very important. It influences how much of our power will be real and how much of our power will be imaginary. And finally, you'll notice that if we write complex power in rectangular form, we have these terms P and Q. So the real part of our complex power in rectangular form is the average power, or real power. So whatever the real part of our complex power is, that's our average power P. So whatever real power we have, that is P. That's the usable power that we can take from our circuit. The Q term, or reactive power, is the imaginary component of our complex power in rectangular form. So we see that this Q is basically the reactive power, and P is the average power, or the real power. So in a DC circuit, we only see real power P, but in an AC circuit, if we have inductors or capacitors in there, we're also going to get some reactive power Q due to the imaginary components. So all these equations are extremely important. Please make sure you keep this table handy, and definitely take the time you need to practice using these equations in our next homework assignment. You'll see that once you get the hang of complex power, it's actually very straightforward. But it can take a little bit of getting used to when working with these new equations. So let's talk just a bit more about power factor and power factor angle. We saw that the average power P depends heavily on that cosine of theta V minus theta I. This term is so important that we call it the power factor. And then the power angle, or power factor angle, is just the theta V minus theta I difference. We'll see that for any given circuit, the power factor is going to be some constant between 0 and 1. The power factor tells us how much of our power will be real. And more importantly, how much of our power will be actually usable to us. We'll see in our later videos that in order to get as much power as we can from our circuits, we want our power factor to be as close to 1 as possible in order to get the maximum amount of real power in our system. Another really important term comes up when we work with complex power. Suppose we had a power factor of 0.8. We define power factor as cosine of theta v minus theta I. So we could say 0.8 must be cosine theta v minus theta I. So if I solve for theta v minus theta I could say theta v minus theta I is inverse cosine of 0.8. But if you look at inverse cosine of 0.8, there's two possible answers. Our difference here, theta v minus theta I, could be either positive or negative 36.87 degrees. We need to make sure it's very clear which one is the correct answer. To do this, we specify these terms leading and lagging. And we always specify whether our power factor is leading or lagging relative to the voltage. So make sure you remember these terms. So if theta v minus theta I is greater than 0, we say that our power factor is lagging. If theta v minus theta I is less than 0, we say that our power factor is leading. This allows us to determine which of those two possible results is our actual power factor. And from there, we can determine the values of theta v and theta I. Let's try a couple quick examples. Suppose I say my power factor is 0.8 leading. If you remember, leading means that theta v minus theta I is less than 0. So in this case, I know that theta v minus theta I must in this case be negative 36.87 degrees. On the other hand, if my power factor is 0.8 lagging, then I know theta v minus theta I is greater than 0. And so for a lagging result, I would see theta v minus theta I must be the positive value from that inverse cosine. Finally, you may be wondering, well, what's the physical significance of all this stuff anyway? Why do we care about leading and lagging and P and Q and S? It turns out that all these values are interrelated, and they influence how much power we are able to deliver in an AC circuit. To help us visualize what's happening, we often draw a phasor diagram like this one. We see that the average or real power that we can actually use is given by the real component of our complex power. The imaginary part, or reactive power, is based on the vertical component of our imaginary plane. And then our apparent power, S, will be the magnitude of our entire complex power phasor. And in our next videos, we're going to look at how we can apply corrections to reduce the reactive power and get more real power out of our circuit. Generally, our goal is to minimize the amount of reactive power Q that we have and maximize the amount of real power P. Because the real power P is the stuff that we can actually use. Imaginary power is dissipated by the inductors and capacitors, and not directly usable for us. In our next video, we're going to take a closer look at what happens when we change our power factor angle. Here's a preview. Our ideal case is when our power factor angle is 0. This happens when our current and voltage phasors are in phase with each other and have the same phase angle. This is the ideal case because we transfer 100% of our power, and our power is 100% real. So ideally, we want our current and voltage phasors to be in phase. This will allow our circuit to behave as if it has just a resistive load. But we'll see later that most of the time, we can never be in this perfect ideal case. Usually there's going to be a little bit of reactive power. We'll see that if our power factor angle is less than or greater than 0, our circuit and its load will behave either like a capacitor or an inductor. If we end up with case 2 or case 3, then we can consider applying corrections in order to reduce that imaginary power Q and increase the amount of real power that we receive. We'll take a closer look at this in our next video. Let's go ahead and finish up with one last example, and then we'll practice complex power in more detail in the next video. In this example, we are asked to determine the average power and complex power delivered to each element in the circuit. We are also told that our source voltage is 100 cosine 1000 t volts. In the second part of our question, we are told to verify that power is conserved. So if we say power is conserved, we want to show that the power supplied by the source is equal to the power received by all the components. So let's go ahead and give this question a try. Let's first talk strategy. How should we approach this question? How can we find average power P and complex power S equals P plus JQ for each component? Here's a very helpful strategy. Remember that important complex power equation. We know complex power S is going to be VI star divided by 2. So basically, we need to first find V and I delivered to each component. Once we know V and I, we can use V and I to calculate S. Remember, that's our complex power. And remember, if we want the real power, or the average power P, is just the real part from S equals P plus JQ. So all we need to do here is first find V and I, use V and I to calculate complex power S, and then just take the complex power and average power directly from those results. So let's go ahead and give all this a try. Let's go ahead and find V and I for each component. Well, to do that, I first need to convert to frequency domain. Let's see what we get. We're given our source voltage is just 100 angle 0 degrees volts. And then we can find the impedance of each component in our circuit. So notice our omega here is 1,000 radians per second. So we know the impedance of our resistors is going to be 10 ohms, because that's frequency independent. But down below, we know the impedance of our capacitor is 1 over j omega c, or 1 over j times 1,000 times 100 times 10 to the minus 6 farads. That gives us negative J10 ohms. Finally, our inductor is equal to J omega L. We determine that impedance will be 1,000 times 20 millihenries. This gives us plus J20 ohms. So now we have everyone in frequency domain. Now we can calculate our current I. Remember, V equals IZ, so our current I must be our V, 100 angle 0 degrees, divided by J20 plus 10 minus J10 ohms. If we go ahead and simplify this, this is 100 angle 0 degrees divided by 10 plus J10 ohms, or 100 angle 0 degrees divided by 14.14 angle 45 degrees. So our current I is going to equal 7.07 angle negative 45 degrees. So now we know I equals 7.07 angle negative 45 degrees. And we know Z of each component. So now we can find the voltage delivered to each component using V equals IZ. Then we can use S equals V I star divided by 2 to get the complex power for each component. So let's go one by one through each component. Let's find voltage and complex power. Let's start with the resistor. Well, we know the voltage across the resistor is just going to be I times the impedance of the resistor. And that's just going to be 7.07 angle negative 45 degrees. Remember, that's my current. And the impedance of my resistor is 10 angle 0 degrees. If I multiply through, I will get 70.7 angle negative 45 degrees. So now I have my voltage, so I can say the complex power delivered to my resistor is the voltage times I star divided by 2. Remember, I star is our complex conjugate of I. So in this case, I go ahead and substitute in. My VR is 70.7 angle negative 45 degrees. I star is 70.7 angle plus 45 degrees. So notice here, the I star is 7.7 angle negative 45 degrees times negative 1. Remember, for complex conjugate, we flip the sign on the imaginary part of our number. So if I perform that calculation, I determine that the complex power of my resistor is, oops, and I wrote the current wrong. Notice the current here is 7.07 because our current is still 7.07 amperes. So if I multiply the 70.7 volts times the 7.07 amperes, I'm going to get 500 for my magnitude. Negative 45, positive 45 give me 0 degrees divided by 2. So I determine my complex power across my resistor is 250 angle 0 degrees, or 250 plus J0 volt amperes. Let's continue for the rest of our components. For our inductor, we can use a similar approach. Let's start with our inductor's voltage. We know the voltage of our inductor is our current I times the impedance of that inductor. So if we go ahead and calculate that, we know our current I is 7.07 angle negative 45 degrees. And then you'll remember our inductor has 20 angle 90 degrees as its impedance. Again, that just comes from our plus J20 ohm impedance. And if we multiply those two together, we will determine that the voltage across our inductor is 141.4 angle positive 45 degrees. Then, just like before, we can plug into our complex power equation. Remember, once again, we need to take complex conjugate of current. So we plug in. We've got voltage across our inductor is 141.4 angle positive 45 degrees volts. Our I star value is 7.07 angle positive 45 degrees because we took our complex conjugate. We divide by 2. We end up getting 1000 angle 90 degrees divided by 2, which gives us 500 angle 90 degrees, or 0 plus J500 volt amperes. Notice how the complex power for the inductor is completely imaginary, whereas the complex power for the resistor is completely real. Finally, we have our capacitor. We know the voltage across our capacitor is current times the impedance of our capacitor. So if we substitute everybody in, well, we know our current is 7.07 angle negative 45 degrees. And remember, our capacitance is negative J10 ohms. We can write this as negative 10 angle 90 degrees, or 10 angle negative 90 degrees. I'm going to go ahead and take the 10 angle 90 degrees form in order to keep my amplitude positive in the polar form. And so if I go ahead and complete that Ohm's law calculation, I determine that the voltage across my capacitor will be equal to 70.7 angle negative 135 degrees. And now I can go ahead, plug into the complex power equation. And if I do that, I plug in my voltage, which is 70.7 angle minus 135, times my current, which is 7.07 angle positive 45, divided by 2. This gives us 500 angle negative 90 degrees, divided by 2, or 250 angle negative 90 degrees, or 0 minus J250 amperes, volt amperes. There's actually one last component we want to check. Remember, we want to show that power is conserved, so let's also look at our voltage source. We know the voltage of our source is given by 100 angle 0 degrees. So the complex power from our source is VI star divided by 2, or 100 angle 0 degrees times 7.07 angle plus 45 degrees divided by 2. And so if we go ahead and calculate that out, we're going to see that our source delivers 707 divided by 2 angle plus 45 degrees power, which is equal to 353.5 angle 45 degrees, or 250 plus J250 volt amperes. So now you can see that we have successfully found the average power and complex power delivered to each element. The average power is just the real part of the complex power. And then, of course, our complex power is the entire expression for the resistor, inductor, capacitor, and of course, our source. All that's left is to show that power is conserved. So basically our goal here is to show that the power received equals the power from the source. We know that our source, as we just calculated, gives us 250 plus J 250 volt amperes. And what's our power received? Well, the power received is equal to the sum of the power from the resistor, inductor, and capacitor. So let's add those together. We know the resistor gives us 250 plus J0 volt amperes. Our inductor gives us 0 plus J500 volt amperes. And our capacitor gives us 0 minus J250 volt amperes. If we combine the real and imaginary parts, we see that we get 250 plus J250 volt amperes. These two quantities are equal, so power is conserved. So that's all there is to it. The key thing with complex power is to keep those toolbox equations handy, especially S equals V I star over 2. These are really important equations, and we'll see in the next video that by optimizing our complex power, we can design circuits that transfer power as efficiently as possible. Let's go ahead and wrap up here for today. By now you should be able to explain the similarities and differences between AC and DC power. We've learned that AC power actually can be calculated in a variety of different ways. In AC circuits, you want to know how to calculate instantaneous power P of t, average power P, complex power S equals P plus JQ, and of course our RMS values, which are basically the equivalent values to the DC power. Finally, we've started to apply complex RMS and instantaneous power to circuits problems, and we'll take a look at more about the physical significance of complex power and more about optimizing power transfer in the next video. Thanks everyone for joining the fun, and we'll see you next time.